pulley over to B and then over to C. And so when C moves a particular distance, then the others move a distance also, but not as far as C. So if you see C has like one rope attached to it, as it moves 1 meter, that 1 meter length has to get distributed amongst all those others. Okay, so the other blocks B and A are going to move at a smaller, different displacement than C. And it's actually easier to look at a 2 system right now. Okay, so we'll look at this one. And so A is the one, this again is a complete pulley. Okay, and so A is going to move, let's say, 1 meter down. Then how far do you think B is going to move up? So this has one rope, and that 1 meter then has to be dispersed between 2 sides of this. So if this moves 1 meter down, this is going to move half a meter up. Okay? Because that length of rope gets distributed on 2 sides of that pulley. And so if you take the derivative of that displacement, you get velocity. So if this moves at 2 meters per second downward, then it's going to move at 1 meter per second upward. And then the same thing with acceleration. If it's accelerating, wouldn't accelerate 10. Let's say it accelerates 5 meters per second squared downward, then B is going to accelerate 2.5 meters per second upward. So that's pretty much the gist of this dependent motion. Basically, those go in there. So when you have multiple ones together, then it gets a little more complicated. You have to know two displacements and or 2 velocities or 2 accelerations. So kind of the same thing here. So as in light of that, this is another example you could probably answer. So velocity of A is 6 meters per second to the left. What do you think the velocity of B is equal to? Count the number of ropes across.
So 2.
Yes, so 3 meters per second divided by, 6 meters per second divided by 3 ropes would give you 2 meters per second. Okay, and that's kind of similar to those pulley systems. Remember, like if this were a pulley system and this were 100 newtons downward, and you have these 3 ropes and it's in static equilibrium, and you have the 3 ropes pulling up, each rope would carry 100 over 3 newtons. So kind of a similar type concept there. Do you remember the graphical? So if I think I talked a little bit about this. If we're given position as a function of time, the slope at x2 is equal to the velocity at x2, right? And then the slope of the velocity curve is equal to the acceleration at time t2. So if you're differentiating, you have your slope is equal to that slope is equal to that. If you're going from acceleration and integrating to get velocity, then the integral is basically the area under the curve. So if you want to, let's say this is 0 seconds, and you want to find your velocity at point 1, then what you do is you look at this area. Let's call that V1. Okay. So this area here is the velocity at 1. It is that value over there. Okay. Then if you want to find the velocity at point 2, what you do is you take, again, that total velocity, and that would give you the velocity at V2. This V1 would give you V1. This would give you, so that's V2, and that would give you V1 and V2. I didn't want to put that under there, okay? So anytime, if you're given the curve of acceleration, you can find instantaneous velocities by figuring out what the area is under that curve at that particular point. So if you wanted to find the velocity at T3, then you would take
entire area,
that total area, and you would add to it to that initial velocity. And you can do the same thing. Same relationship holds between velocity and position. And so if we wanted to find the position at x1, then this would be the area under that curve would be the value of x1. Okay? And then the area under this curve would actually be the difference between that two, but the total area would be the value of x2. Okay? So if you're differentiating slopes, if you're integrating, the value of it is the area under the curve. Did you do that for like shear and bending moment diagrams to?
Yeah.
Yeah. That relationship. All right, I guess before these slides they were all one-dimensional, and so now things are moving in 2 dimensions, which is just called, rather than rectilinear motion, it's called curvilinear. And so we can use some curvilinear motion. We can use that Cartesian vector format. So our coordinate system can be x and y, and then if we have 3 dimensions, it could be z also. So we could use that coordinate system. And what types of motion do we use Cartesian vector format for? So projectile motion. Okay, because we can split the acceleration in the y direction and the x direction independently, and then it's very easy to use that Cartesian vector format. So this just shows kind of these slides here, that instead of x as a function of t, we're going to have r as a function of t. Okay, and this, if we're using rectilinear motion, we'll have I, j, and k components. So let's say this is 3t squared I plus 4t cubed j. Okay, so then if we keep going on and we look at those points as they get closer to each other, then take the limit as t goes to 0, then the velocity is equal to dr dt. Okay? And because the position is, each direction is independent of each other, the I, j, and k directions, we can just take the derivative directly. So this would be 6t I plus 12t squared j. Okay, and then if we wanted the acceleration, obviously it would be the derivative of velocity. Okay, and our acceleration would be 6I plus 24t j. Okay, so just an extension of our one-dimensional equations, but now we're looking at it in 3 dimensions, and so therefore we put our I, j, and possibly k components there. Okay, so this just develops the relationship between the position r, the r vector, position vector r, and then here we go. We didn't need that many slides to understand that, right? Okay. So, but basically, finally, after the 6 slides here, it came up with these 3 relationships. And if your position is has independent I, j, and k components, you just